There's three ideas that are used to some geometric progressions. The first idea is around subtracting finite things. Let's look at that. Suppose we have some things inside a collection of boxes. Let's call the set of boxes S1. It does not matter what is inside each box. It could be cats, dogs, or mathematical terms, but it is finite. We have another set of boxes. Let's call that set of boxes S2. S2 has all boxes of S1 except the blue box, but it has the pink box that S1 does not have. Idea 1. To get S2 minus S1, we do not need to know the value of S2 and S1 themselves. S2 minus S1 is the pink box minus what's inside the blue box. Boxes inside the yellow lines are in both S1 and S2 and they don't affect S2 minus S1. Or, S2 minus S1 equals what only S2 has minus what only S1 has. Idea 2. If there is a clear relationship between the terms of two series, then the sums of the series may also have the same relationship. For example, term 1 of series 2, the blue box, is some constant k times term 1 of series 1, the light blue box. Term 2 of series 2, the red box, is some constant k times term 2 of series 1, the light red box. Term 3 of series 2, the green box, is some constant k times term 3 of series 1, the light green box. And so on. Since each of the boxes in series 2 is a constant k times that of a corresponding box in series 1, we should expect series 2 to sum to k times series 1. Now let's use those ideas to some geometric progressions. Suppose we have a geometric series with starting term a. Second term is a multiplied by r with common ratio r. Third term is a multiplied by r squared. And so on. Until term n, which is a multiplied by r raised to n minus 1. Let's use idea 2 and construct series S2, whose term k is equal to term k of S1 multiplied by r. First term of series 2 is the first term of series 1, a multiplied by r. Term 2 of series 2 is ar power 1 multiplied by r, or ar power 2. Term 3 of series 2 is ar power 2 multiplied by r, or ar power 3. And so on. From idea 2, we know that sum for S2 must equal r times sum of S1. Or sum of S2 minus sum of S1 must equal r minus 1 multiplied by sum of S1. Now let's use idea 1. Except for the first term of S1, S2 has every term S1 has. Also, S2 has exactly one term that S1 does not have, ar to power n. What is inside the yellow lines is common to both. So sum of S2 minus sum of S1 must be a multiplied by r power n minus a. So sum of S1 multiplied by r minus 1 must equal ar power n minus a. So sum of S1 must equal ar power n minus a divided by r minus 1. A better way to remember that is, sum of geometric progression is the last term multiplied by common ratio minus the first term divided by common ratio minus 1. Review of key learnings. 1. To know S2 minus S1, we don't need to know the values of S2 or S1. We need to know what only S2 has and remove what only S1 has. What is common to both S1 and S2 does not affect S2 minus S1. 2. Creating a new series S2 equals S1 multiplied by common ratio, and taking the difference, S2 minus S1, gives some GP equals term that only S2 has minus term that only S1 has divided by common ratio minus 1. 3. The term that only S2 has is the last term of S1 multiplied by common ratio. So sum GP equals last term multiplied by common ratio minus first term divided by common ratio minus 1. 4. Caution: for the moment we are not dealing with infinite series, they don't have a last term, but the ideas above hold, so long as the sum is finite.